Hello and welcome to this explainer. Today we're diving deep into a rigorous, highly analytical journey. Our core objective here is absolutely crucial. We're going to establish the precise mathematical link between microscopic single crystal mechanics, literally how individual atomic planes slip, and the macroscopic yield strength we observe in bulk polycrystalline materials. We're going to build this causal chain step by step, entirely from the ground up.
So here is the deductive roadmap for our analysis today. We'll start with single crystal work hardening, move into the geometry of slip activation, explore the kinematics of lattice rotation, unpack the von Mises yield criterion, and finally synthesize it all with macro yield and the Taylor factor.
Let's jump right into Section 1, single crystal work hardening and the triphasic sequence. We need to start our first analytical phase by establishing a solid baseline. How does an isolated, single crystal actually behave under stress?
Think about the fundamental macroscopic stress-strain response of a single crystal. The curve is universally defined by a profound triphasic work-hardening sequence, which we categorize as stages I, and 3. What makes this so compelling is that this exact three-part shape is inherently dictated by the crystallographic orientation aligned parallel to the stress axis.
To truly understand the mechanics behind that curve, we have to look at the work-hardening matrix. If we systematically break this down, stage 1, often called easy glide, features a negligible or constant hardening rate. Why? Because we essentially have a single active slip system with very minimal dislocation interaction. But as stress increases, we hit stage 2. Here the hardening rate increases linearly because multiple intersecting slip systems start to activate, and that leads to extensive complex dislocation interaction. Finally, in stage 3, the curve becomes parabolic. The hardening rate actually decreases because high levels of stress force extensive cross-slip, which, interestingly enough, relieves some of that internal stress.
However, it's important to remember that this idealized sequence is highly sensitive to both intrinsic and thermodynamic factors. On one hand, increasing the temperature provides thermal energy that facilitates premature cross-slip, which effectively shrinks stages I and 2 and lowers the critical resolved shear stress. On the other hand, particularly in face-centered cubic or FCC metals, decreasing the stacking fault energy creates wider stacking faults. This statistically inhibits cross-slip. A brilliant real-world example of this is copper with 30 atomic percent zinc. Its extremely low stacking fault energy forces stage 2 to extend to notably high stress levels before stage 3 can ever even initiate.
Moving on to Section 2, geometry of slip activation and the Schmid factor. Having seen the stages of hardening, we have to ask, what actually triggers a crystal to transition from elastic loading into plastic deformation?
Well, the geometric constraints are quite clear. The orientation of the slip plane and the slip direction relative to the applied load axis determines the exact threshold of yielding. We define this precise geometry using 3 specific angles. First, there's phi, the angle between the tensile axis and the slip plane normal. Then, lambda, the angle between the tensile axis and the slip direction. And finally, chi, the angle between the slip plane itself and the tensile axis. And a quick mathematical note here, phi plus lambda does not necessarily equal 90 degrees.
From those core geometries, we can mathematically deduce Schmid's law step by step. Step 1, we calculate the normal stress acting perpendicular to the slip plane. Step 2, we calculate the resolved shear stress, or RSS, which is the stress acting generally across that plane. Step 3, we isolate the specific shear stress acting exactly in the active slip direction. We call this the critical resolved shear stress, or CRSS. The absolute crucial takeaway here is that macroscopic yielding is not some arbitrary event. It happens precisely when the applied stress resolves into a critical shear threshold that is entirely intrinsic to the material's atomic bonds.
Let's transition into Section 3, kinematics of lattice rotation, exploring physical constraint and dynamic geometry. So we know the threshold for yielding, but what dynamically happens the moment after that critical threshold is breached and slip actually activates?
Think carefully about the physical reality of tensile testing. If a sample were completely unconstrained in a vacuum, crystalline planes would just glide freely, essentially bending without rotating the lattice at all. But in physical reality, tensile machines firmly grip the sample ends, enforcing a strict vertical alignment. Because the atomic planes can't just slide laterally out of the machine grips, the internal crystal lattice is physically forced to rotate toward the tensile axis as the material elongates.
And we can define this constrained rotation with mathematical rigor.
The underlying equations prove that glide shear strain and resolved shear stress are strict mathematical functions of both the initial slip orientation and the macroscopic extension ratio. To put it simply, strain hardening is inextricably mathematically linked to continuous geometric rotation during deformation. In a constrained system, you literally cannot have one without the other.
Because this lattice is rotating dynamically in three-dimensional space, and because we know orientation dictates those Schmidt factors, we absolutely must track this movement. We do this using a stereographic projection. Think of this map as a tool that allows us to precisely trace the relative position of the tensile axis as the internal lattice physically rotates beneath it during continuous deformation.
As the lattice rotates, that tensile axis maps steadily toward the primary slip direction. Eventually, it hits a boundary of symmetry where a conjugate slip system becomes equally favored to activate. But here is a truly fascinating complication, the overshoot phenomenon. Because of latent hardening, where the active slip plane gets heavily congested with tangled dislocations, the initial system strongly resists yielding its dominance. So the axis physically overshoots that symmetry line. Ultimately, the stress forces the conjugate system to activate anyway, and the result is an alternating slip pattern until the material finally fails.
Section 4. The von Mises yield criterion and polycrystalline constraint. Up to this exact point, we've only been discussing single, isolated crystals. We must now translate these geometric rules into a real-world polycrystalline matrix. In a bulk structural metal, single grains cannot deform in isolation anymore. They are totally surrounded by grain boundaries, which creates a very strict structural boundary condition. Take adjacent grains A and B, for example. The strain generated along their shared boundary must be mathematically identical in both grains to maintain structural continuity. If they try to deform differently, microscopic gaps or overlaps will occur, and that results instantly in catastrophic brittle fracture.
To achieve this identical strain and stay intact, grains need options, specifically multiple slip systems. But we have to be incredibly careful with the geometry here. Take a hexagonal close-packed, or HCP, structure. It has 3 physical slip directions on its basal plane. However, any physical displacement in one direction can be perfectly replicated by a linear combination of the other 2. Therefore, mathematically speaking, HCP exhibits only 2 genuinely independent slip systems. This inherently predisposes it to brittle fracture unless higher temperatures can step in to activate secondary systems.
So, the big question is, how many independent systems are actually required for unbroken polycrystalline deformation? We use the von Mises criterion to find out. Step 1. We define an arbitrary plastic deformation using a strain tensor, which inherently has 6 independent components. Step 2. We apply the fundamental law that plastic deformation occurs at a constant volume. Step 3. Because volume is conserved, the 3 diagonal components of our tensor are mathematically bound to sum to exactly 0. This elegant mathematical necessity eliminates 1 degree of freedom. 6 minus 1 leaves exactly 5. Therefore, unbroken, arbitrary plastic deformation strictly requires a minimum of 5 independent slip systems.
Finally, Section 5, macro yield and the Taylor factor. This is where we bridge the micro and the macro. We have the microstructural mechanics, and we have the boundary constraints. Let's synthesize this into overarching macroscopic engineering data. Now, in a highly textured polycrystal, the internal grains are not randomly oriented. Because every single grain possesses a unique Schmidt factor relative to the applied load, they absolutely do not yield simultaneously. The grains with the lowest Schmidt factors geometrically resist deformation the longest. They act essentially as internal structural reinforcing elements within the microstructural matrix, literally holding the material together until the global stress is high enough to force cooperative systemic yielding.
And this brings us to the ultimate unifying metric of our explainer, the Taylor factor, denoted mathematically as M. The Taylor factor is the key that allows us to directly mathematically relate the macroscopic uniaxial yield stress of a bulk metal to the microscopic critical resolved shear stress of its atomic planes. It is the mathematical average of all those orientation factors required to maintain that unbroken 5-system minimum cooperative deformation across every single grain in the matrix.
The magnitude of M basically serves as a direct multiplier of intrinsic strength. For instance, highly symmetric FCC structures possess a standard average Taylor factor of approximately 3.06. Body-centered cubic or BCC structures average around 2.75.
This proves mathematically that the geometric constraint of grain boundaries fundamentally results in an inherently higher resistance to plastic flow than the base atomic bonds alone would suggest.
Synthesizing our entire causal chain, the polycrystal stress-strain curve is not a separate physical phenomenon from the single crystal curve. They are intrinsically linked. It is the exact same microscopic physical mechanism, dislocation glide, scaled mathematically by the geometric constraint of the Taylor factor. Macroscopic stress is simply single crystal shear stress multiplied by 3.06. Internal crystallographic geometry strictly and mathematically dictates external macroscopic strength.
We have established an unbroken mathematical chain today, starting from a single atomic slip plane all the way to the yield strength of a massive steel beam. But I want to leave you with this provocation. If internal crystallographic geometry fundamentally dictates external strength, how precisely can we, as engineers and materials scientists, begin to intentionally process and engineer specific microscopic textures to selectively manipulate the extreme macro yield behavior of next-generation structural alloys? Think about that causal chain and what it truly means for the future of advanced materials engineering. Thank you so much for joining me for this explainer.